Hello everybody and welcome. My name is Willem Röpke and today I will be presenting our work, which is titled On Nash Equilibria for Multi-Objective Normal Form Games under Scalarized Expected Returns versus Expected Scalarized Returns. Now this is work that I've done mostly from within the context of my master thesis under the supervision of my wonderful co-authors Diederik, Anne and Roxana. First, a bit of motivation. Why is this actually interesting to study? Well, if you look out at the real world, there are many examples of problems in which there are both multiple agents as well as multiple objectives. Then in game theory, we take a look at these types of problems through the lens of multi-objective games. Now, with the types of games that we consider in this work, and specifically using the approach that we do, we have different optimality criteria. And previous work has actually shown that these different optimality criteria are not equivalent in general, but their relationship between these criteria is still unknown in a number of situations. So this led us to conclude that there is more work needed from a theoretical perspective. And that is exactly what we will be discussing in this talk. So we will give a theoretical study of Nash equilibria in a team reward but individual utility setting. And I will explain in a minute what all of these terms actually mean. Concretely, we will first study the existence and relationship between Nash equilibria under both optimality criteria. And secondly, we will study pure strategy Nash equilibria under both criteria and see how they relate to each other. In total, we will formally show 5 new properties during this talk. I also want to give a bit of background because that might also be important to follow this presentation. So in this work, we consider multi-objective normal form games. They have already been around for a very long time. They were introduced in the 1950s by Blackwell, and you could intuitively understand them as the multi-objective counterpart to single-objective normal form games. I also contribute here a formal definition of a multi-objective normal form game. So it is a tuple where you have n that is a finite set of players indexed by I. You have A, where each AI is a finite set of actions available to player I. And then you have P, where each PI is a vectorial payoff of player I. And this is in contrast to single objective normal form games where each PI would be a simple scalar payoff. Now, I have also added to the right a quick example of such a multi-objective normal form game with 2 players, a red player and a black player. And if the 2 players take an action, they will always end up in one of these squares. So for example, if they both take action A, they will end up in this square, and then the red player will receive a vectorial payoff of 1 and 1, and the black player will receive a vectorial payoff of 0 and 0. Now, important to note is that in this case, both players receive an individual reward, but it is also possible that they receive the same reward in each case, and then we will call this type of setting a team reward setting. Also in this paper, we take a utility-based approach, and that means that each agent has a different, possibly different utility function. Now, what is a utility function? A utility function is a function that takes an incoming reward vector and scalarizes this to a final scalar utility. Now, as I just mentioned, these utility functions may be different for each agent in the game, and they may also be nonlinear. Now, the utility-based approach and these vectorial payoffs bring with it an interesting question, namely, what should we optimize for? Because there are actually 2 optimality criteria, and let me illustrate this with a quick example. Say you are a commuter and you want to go to your work in the morning and you want to optimize your travel with regards to 2 objectives. First, you might want to optimize for the level of comfort, and second, for the speed or for the time it takes you to get to your destination. You might say, well, I want to optimize the utility that I can derive from each individual trip, or in more definitive terms, the utility that I can derive from each individual policy execution. And in that case, you would be optimizing for the expected scalarized returns, for which I present a brief definition here. But on the other hand, you could say, well, I'm going to make this trip every day for the foreseeable future. So what I actually care about is the utility that I can derive from the average payoff from several executions of the policy. So the average payoff from several of these trips. And in that case, you would want to optimize for the scalarized expected returns, or in short, the SER criterion. Now, important to note here is that it has been shown that in a multi-objective normal form game under the ESR criterion, you can effectively reduce the multi-objective normal form game to the scalarized single objective normal form game. All right? And then moving on, in this paper, we specifically take a look at Nash equilibria. So first of all, what actually is a Nash equilibrium? It happens when no player can unilaterally deviate from the joint policy and still improve. And we can define it actually in terms of SER and also in terms of ESR. So under SER, it is a joint policy from which no player can unilaterally deviate and still improve the utility of their expected returns. Under ESR, however, it is a joint policy from which no player can unilaterally deviate and still improve the expected utility from the returns. And the last thing that I want to note here is that it has been shown in previous work by my co-author Roxana that if you have a multi-objective normal form game under the SER criterion, there need not necessarily be a Nash equilibrium in the game, which is in stark contrast to results from single objective normal form games that has been previously shown to include at least one mixed strategy Nash equilibrium in each game. All right, so moving on to the actual contributions of this work. The first theorem talks about the occurrence of Nash equilibria, and specifically it says that in a multi-objective normal form game with at least one Nash equilibrium under both criteria, the size of the sets of Nash equilibria under the scalarized expected returns criterion and under the expected scalarized returns criterion need not be equal. So in short, the number of Nash equilibria under SER and ESR can be different even when both have at least one Nash equilibrium. And we were able to show this by constructing a game with this exact property. I show the game here. In this game, both players use the same utility function that I show here for two objectives, the X objective and the Y objective. And here you see then the multi-objective normal form game itself. And to the left, we show the game under the SER criterion, so with the multi-objective reward factors. And to the right, we show the same game, but under the ESR criterion, where we have applied the utility function a priori. And so here we have the scalarized utility for both agents. All right. And so recall that we want to prove that the number of Nash equilibria is not the same even when both have Nash equilibria. And we start proving this by first talking about the right-hand side. Because this has been reduced to a single objective normal form game, we can use techniques and algorithms from single objective normal form game theory and prove or show or calculate all of the different Nash equilibria in this game. And it turns out that there is only one Nash equilibrium, namely the pure strategy AA. And it is also fairly intuitive to notice, because if both players play AA, there is no incentive to deviate to playing B. And if both players play BB, there is some incentive for either agent to play A. And if one agent plays A, the other agent automatically also wants to play A. So there is exactly one Nash equilibrium. And here on the left-hand side, what we now want to prove is that there are at least two Nash equilibria. And we are able to prove that indeed there are at least two mixed strategy Nash equilibria. If one player, for example, always plays A, then the best response for the other player would be to play A with probability 11/20 and B with probability 9/20. And if the second player then plays this strategy, then the original player will still want to play A all the time, meaning that we have arrived at the Nash equilibrium. And if the players switch positions, it is indeed again a Nash equilibrium. So we've been able to prove the first theorem. Now the second theorem goes a bit further and it talks about sharing of Nash equilibria. And what it says is that in a multi-objective normal form game with at least one Nash equilibrium under both criteria, the set of Nash equilibria under the SCR criterion and the set of Nash equilibria under the ESR criterion may be disjoint. So in short, what this means is that no equilibrium is necessarily shared under both criteria. And we again show this by construction. So if we use the same construction as before with exactly the same game and utility functions, we know here that we have exactly one Nash equilibrium, namely AA. But on the other hand, we had at least two mixed strategy Nash equilibrium, but AA is not a Nash equilibrium, because if one agent plays A, the other player will always be inclined to play the previous best response that I've just mentioned. Now we will move on to the last set of contributions of this work, namely we take a look at pure strategy Nash equilibria. And first we take a look specifically at how pure strategy Nash equilibria relate going from SCR to ESR. To kick things off, we had to come up with a quick lemma that states that if you have a pure strategy profile, the following holds. So the utility of the expected returns is the same as the utility of the returns is the same as the expectation of the utility of the returns. And this holds because if you have a pure strategy profile, your payoff will be constant, and the expectation of a constant is always that constant. All right? And that brings us then to theorem 4, which says that if you have a multi-objective normal form game, then a pure strategy Nash equilibrium under the SCR criterion must necessarily also be a Nash equilibrium under the ESR criterion. And the crucial insight to arrive at this is that, well, if you have a pure strategy Nash equilibrium, that must necessarily be better than any other pure strategy. But then it must also be better than a mixture of these pure strategies, because a stochastic mixture can never be better. And I show the proof here. I will quickly go over it, not in detail, but rather quick. There is of course, more detail in the text. So, given a pure strategy Nash equilibrium under SCR, we can say that, first of all, we write the definition of such a Nash equilibrium. Then, in the second line, because we have just shown lemma 3, we are able to remove this expected value here. Then, in the following line, we want to explain that, well, if the utility for this pure strategy is better than any other strategy, it is also better than playing any other pure strategy. And if that is the case, it must also be better than a stochastic mixture of either of these pure strategies. And then lastly, we can rewrite this left-hand side to again include this expectation, as we've shown in the lemma, and the right-hand side to this form, and then we arrive at the definition of a pure Nash equilibrium under ESR. Now you might wonder, does the inverse direction also hold? And we're very sad to say that no, it actually does not. So if you have a multi-objective normal form game, a pure strategy Nash equilibrium under the ESR criterion need not also be a Nash equilibrium under the SCR criterion. And we actually are able to give a counterexample that this is not necessarily the case. And we can actually use a counterexample, we use a construction that we made before. So if we again take the counterexample, sorry. If we again take this counterexample, you here have the utility functions. And if you recall here, there was a pure strategy Nash equilibrium AA. However, if we then go back again to the multi-objective reward factors under the SCR criterion, AA is not a Nash equilibrium, so the inverse indeed does not hold. Now, lastly, we are able to actually prove that in a multi-objective normal form game, if you say that all utility functions are convex, so if you make that additional assumption, then a pure strategy Nash equilibrium under the ESR criterion is also necessarily a Nash equilibrium under the SCR criterion. And the crucial insight to arrive at this result is that you can use Jensen's inequality and then use a transitive property that says if A is less than B and B is less than C, then of course A is also less than C. Again, I show here the proof. So we start with Jensen's inequality that says if we know that UI is convex, then the expectation of the utility is larger or equal than the utility of the expectation. Now, then, if we have a pure Nash equilibrium under ESR, and if each utility function is convex, then we can first write again the definition of a Nash equilibrium under the ESR criterion. Then in the next line, we can move this expectation inwards because of lemma 3 that stated that this expectation can be moved inwards. Next, because of Jensen's inequality, we can add actually a last term to this inequality. So we add this term here. And then in the last step, because of this transitive property, we can remove the middle term, and now we arrive at the definition of a pure Nash equilibrium under SER. All right, so that brings us to our conclusion. So I want to leave you all with a conclusion and maybe some directions for future work. In this paper, we've taken a look at Nash equilibria in multi-objective normal form games under 2 optimality criteria. And specifically, we have proven 5 new properties relating to the occurrence and relationship of Nash equilibria, and specifically also about pure strategy Nash equilibria under both criteria. Now, we hope that these new insights and proofs give a possible basis for future algorithmic approaches, and in the future we actually want to create such algorithms. But we also want to study settings in which agents may have different optimality criteria. Because if you take a look at all of the proofs given here, we assume that each agent in the game is optimizing for the same criterion, but that is not necessarily the case. So it might be interesting to also look at such type of settings. And lastly, we want to study what happens when you add different restrictions. So now we have added in the last theorem a restriction on the type of utility functions. Namely, they must also always be convex. But for example, it would be interesting to study when you add restrictions on the type of payoff structure or different utility functions that may occur. And so that concludes this talk. I hope you've enjoyed it. If you have any questions, remarks, or even some brilliant ideas, you are very free to shoot me an email. My email address was at the first slide. And I hope you've enjoyed it, and I wish you all a wonderful day. Bye!